Yes, Mohammed. Hi. Can you able to see the board? Okay. Mohammed, can you able to see the board? Who all are joined? Just say hi. Mohammed, you are only one, no? Joined. Are you there? Mohammed, can you able to hear me? Who all are joined? Just say hi. Okay, Rujul. Okay, we will wait for 1 minute and then we can start. Okay, today we are discussing about the gravitation chapter. Okay, so we are doing some derivations from this chapter. Okay, so we can start with Newton's law of gravitation. We know that the everybody in the means any body is there on the earth that is get attracted towards the earth center. Okay, so each body is what attracting towards the earth, and there is some force is acting on the body from the earth, and that force, that attraction or force of attraction is directly proportional to the product of the masses. F is directly proportional to the masses, okay, m1 and m2, because force of attraction is there in between two bodies, and even force is also inversely proportional to the square of the distance between them. Okay, and if you combine both the statement, then force is directly proportional to m1 m2 upon r square, and if you remove this proportionality constant, F is equal to g m1 m2 by r square. So this is nothing but Newton's law of gravitation, where m1 and m2 are the masses and the r is the distance between them. So product of masses are directly proportional to the forces, and the distance between the two bodies, that is square of the distance between two bodies, are inversely proportional to the force. Okay, and here g is a proportionality constant, and g is also known as a gravitational constant. Okay, and this gravitational constant value is nothing but g is nothing but 6.67 into 10 raised to 11 Newton meter square per kg. Newton meter square per kg square. Okay, so this is the unit and dimension units for the g, and standard value is 6.67 into 10 raised to minus 11. Okay, and if we calculate the dimensions, so write down the dimensions for g. G is nothing but m raised to 1, m raised to 1, l raised to 3, L raised to 3, and T raised to minus 2. Okay, sorry, here M is minus 1 and T raised to minus 2. So these are the dimensions for gravitational constant G. Okay, and G is not dependent upon the nature and size of the bodies. Okay, as well as it is independent of the nature of the medium. It's very important. They used to ask the question based on this. Okay. So they are asking the MCQ question whether G is depend on the any size or nature. It's not. Okay, it is independent of the nature as well as size of the body, and is also independent of the nature of the medium. Doesn't matter what medium is there, how is the nature of the body, that doesn't matter over here. Okay, so that's what G value everywhere, it will remain same. Okay, and suppose here if we have a unit masses and the distance is r is equal to 1. Suppose we have m1 is equal to m2 is equal to 1 kg and distance is nothing but 1 meter. So if we substitute here 1 and 1 upon r square, that is also 1. 1 square is 1. So you will get force of attraction between two bodies is numerically equal to gravitational constant. Okay, this is equal to the gravitational constant which is kept 1 unit distance apart. So this is nothing but what? Newton's law of gravitation. Can you getting Newton's law of gravitation? Here if you take any body, there is a force of attraction between the two bodies. So product of their masses is directly proportional to the force and inversely proportional to the square of the distance between them. And I wrote it in the form of equation, and then I introduced the gravitational constant G. Okay, and G is nothing but 6.67 into 10 raised to minus 11 Newton meter square per kg square, and dimensions are m1 raised to 1, L raised to 3 and T raised to minus 2. If the masses are unit 1 kg or distance is unit meter, then the gravitational constant is numerically equal to the force applied. Okay, so we get this equation. We got the dimensional units for gravitation just by rearranging this. Okay, so here G is equal to F r square upon m1 into m2. So if you put the dimensions and units for the force, distance and masses, then you will get that Newton meter square per kg square, and gravitation G is equal to m raised to minus 1, L raised to 3 and T minus 2. Okay, everyone is getting this point? Okay, you can take a screenshot of this. Okay, then we can move towards the gravitation due to gravity, acceleration due to gravity, that is small g. Okay, so we know that there is an acceleration generated whenever there is a continuously changing in velocity. There is an acceleration. Okay, now here we have acceleration due to gravity. So acceleration due to gravity, we know that many times we are solving the numericals and we are taking the value of g is nothing but 9.8 meter per second square. Okay, this we know that, and this acceleration due to gravity g. Okay, the acceleration, this acceleration is what produced in the motion of a body under the effect of gravity. Okay, when you drop any object from a certain height, then that body comes under the gravity. Okay, and that you can, in that case you can observe the acceleration, and this g is also independent of the mass. Very important point. This kind of questions will come for MCQ. So g is independent. G is independent of mass. Getting this? G is independent of mass. Now we have to derive an expression for acceleration due to gravity. Okay. Then there are many variations are there. On the body is kept at certain height. Body we kept it on the surface of the earth, like that. We have a different cases. So we will learn one by one. Okay. So expression. Write down the heading: expression for acceleration due to gravity. Expression for acceleration due to gravity. Okay, so suppose we have this as the earth and whose radius is capital R and body is kept on the surface of the earth. Okay, if we have this body and this body is having mass m, small m, and earth is having a mass capital M and radius of the earth is nothing but capital R. Okay, so here force of attraction, if we apply here gravitational force, just now we did, okay, so that F is nothing but G and product of the masses, mass of the earth is capital M, okay, and there is a force of attraction between this body and and earth, so GMM divided by this R square, okay, this much force is acting between the body and surface of the earth when the body is kept on the surface of the earth. So F is equal to, we will get G, F is equal to GMM upon R square. Okay, so whenever this body is on the surface of the earth, then this weight is also acting vertically downward, that is M into G. Okay, so that F is nothing but what? We have M into G. That force is also there. So now here both the forces are same. Okay, so if we take this as a equation 1 and this as a equation number 2, both forces are same, then you can compare GMM upon R square is equal to M into G. So this mass and this mass is get cancelled and you will get the value for G is nothing but Gm upon R square. This is nothing but acceleration due to gravity when the body is on the surface of the earth. Okay, and here the value of G is nothing but 9.8 meter per second square. Okay, and radius of the earth normally 6,400 kilometer we are considering. Okay, getting this derivation? Can everyone getting this? Okay, so take a screenshot of this. Take a screenshot of this. Now next, variation of acceleration due to gravity at different cases. Okay, so I'll erase this. If everyone, I hope, took the screenshot of this expression for or variation of acceleration due to gravity. Acceleration due to gravity. Okay, so we can take first one, that is effect of height. Okay, effect of height. So here we can take the earth. Okay, and earth is having radius R and having mass m. Okay, in the last case we calculated the acceleration due to gravity when the body is on the surface of the earth. Okay, so now suppose on the surface of the earth this is a point A, and in that case we got small g, that is acceleration due to gravity is nothing but Gm, that is capital M by R square. So now I raised that body to certain height and I kept it at B. Okay, and from A to B this height is h. I took it as this height as a h. So when body is at A, that time I got acceleration due to gravity G, and when I raised this body at certain height at h, and then that time I am getting the acceleration due to gravity is nothing but h dash. Okay, so here also we have a earth whose radius is capital R, whose mass is capital M. Initially when the body is on the surface of the earth, that time we got the acceleration due to gravity small g, and when I raise that body from A to B through some height h, in that case I am getting acceleration due to gravity as a g dash. Okay, so here if I take the acceleration due to, here if I take acceleration due to gravity at point A, okay, so here we can write G is nothing but I got Gm by r square. This is very first, just now I did this derivation. Okay, now if I want to calculate the acceleration due to gravity at point B, okay, how to calculate the acceleration due to gravity over here? Okay, so here at point B, or acceleration due to gravity at point B, can I write this as a G dash G m upon r plus h whole bracket square. Okay, so because now total height of the body which is kept at certain height from the center of the earth, so we are adding this radius, no, this is the radius of the earth, so we are taking this as a center to this height, total height we are taking, so this will come r plus h. Okay, so g dash is equal to gm upon r plus h whole square. Okay, so this is what you can consider as a equation number 2. Now here we are interested, okay, in g dash. So what you can do, you can take division of 1 and 2, or you can write it, divide equation 2 by 1, okay, and then g dash by g is equal to, I can write gm upon r plus h whole bracket square, and here I can write gm upon r square. So gm is get cancelled, and you can simplify this equation as g dash is equal to r plus h upon r whole bracket square. Okay, or you can write g dash into h into g also. Okay, or we can write, we can separate it, r by r is 1 and h by r. So here 1 plus h by r whole bracket raised to 2 into g. Okay, this is nothing but what? Your equation. Sorry. Here division is there. Gm upon this thing. So here your r square will go up. So g dash is equal to r square upon r plus h. So this entire bracket is to 2 into what? G. Okay. So this is nothing but what? Your answer. Getting this? Can you getting this, everyone? Or you can take the r square common over here. If you take here r square common, or if you are writing r upon r plus h whole bracket square into g, then you can write, you can take here, or you can write separately here. Okay, I hope, can I erase the diagram, or I will take here, I will use this space over here. So you can write g dash is equal to, I will take it, I will write it as a r square I will take it as a common, 1 plus you will get h upon r, okay, whole bracket square into g. Okay, r square get cancelled, g dash is equal to, you can transpose 1 plus h by r raised to minus 2 up. Okay, so I will write it as 1 plus h by r raised to minus 2 into g. So this is also okay. Or by using binomial theorem we can expand this again. Okay, if we use the binomial theorem, when r is very greater than the h, okay, means radius of the earth is more than the height, Okay, so in that case we will get this expression as 1 minus h by r into g. So this is nothing but acceleration due to gravity at point B. Okay, so when the distance h is very small as compared to the radius of the earth. Okay, as we are going up, height is increases, then value of acceleration due to gravity here slowly started decreasing. Okay, getting this very important. They will ask the question, as body we are raising at certain height or we are increasing continuously, what is the effect on the gravitation of the earth? So acceleration due to gravity, what is the effect on acceleration due to gravity? As height increases, then acceleration due to gravity is what started decreasing. So this is a derivation for variation of acceleration due to gravity when the object is at certain height h. Okay, understood up to here? Everyone is getting? Take a screenshot. Take a screenshot of this. Okay, so next derivation, effect of depth. Okay, I hope everyone took the screenshot. Then we are going for effect of a depth. That means we are bringing that body inside the earth. Okay, so we are discussing about effect of a depth. Effect of a depth. Okay, so now here we have this earth having radius capital R and mass is capital M. Okay, now we took that body initially at the surface of the earth. Now I brought that body inside the earth surface. Okay, somewhere here I brought that body. Okay, so initially it is at point A, now it is at point B. Okay, this is at point B now. So here we have acceleration due to gravity g. Okay, and here we have at point B we have acceleration due to gravity is g dash. Okay, so here this is a total radius r of the earth core. Okay, and if I brought this body from A to B as a x, okay, from A to B this is x, then remaining this point B to this center, okay, O, this is nothing but what? R minus x. This is what the distance. Okay, so this is total R is what gets divided from A to B and B to A, and we are getting at point B we have acceleration due to gravity, or if you are not getting you can just make a circle. Okay, so here in this with this radius there is what? Some gravitation is there. Okay, so now here when the body is at A, okay, when the body is at A, we know that the acceleration due to gravity g is nothing but we have gm upon r square. Okay, where m is the mass of the earth, g is a gravitational constant, and r is nothing but the radius of the earth. Okay, and suppose rho is the density of the earth. We know that. What is the density? Rho is equal to m by v, or we can write m is equal to what? Rho into v. And what is the volume of the earth? Volume of the earth is nothing but what? The volume of the sphere. Okay, So volume of the sphere is nothing but how much? I will keep rho as it is, 4 by 3 pi r cube. This is nothing but what? The mass of the body when we are bringing towards the point B. Okay. So now here we can take g dash is the acceleration due to gravity at point B, and its depth or its distance from A to B is nothing but here x. Okay. So body B will experience a force only due to a portion of a earth of a radius r minus x. So whenever we are bringing this body from A to B through a distance x, then we can only there is what some force is exerted on the body B due to this portion r minus x portion. Okay, and at point B we have acceleration due to gravity, that is g dash. So here I will write g dash is nothing but gm upon distance is what? From center to point B is nothing but r minus x whole bracket square. Okay. So this is nothing but what? Acceleration due to gravity at g dash. But this is not my answer. Okay. So here mass is we are keeping, means that body came to point B, in that case its mass is m. So this mass just now we calculated when we are taking that body to certain depth inside the earth core. So we are replacing this m dash by rho 4 by 3 pi r cube divided by r minus x whole bracket square. Okay. Can you getting these all steps? Can you able to getting this? Okay. Now here we can make one more change. What is the change? Here I wrote r cube, no? So body is, we bring it at certain depth, and from the center this body B is having radius how much? R minus x. So here I will also replace this r minus x whole bracket cube. So now check here, this square and out of this cube 2 are get cancelled, and you will get g rho 4 by 3 pi r minus x raised to 1, because the bracket which was there in the denominator, that is what get cancelled. Now you can take this as a equation number 2. You can take it this equation as a number 2, and now you can divide equation 2 by 1. Okay. So before dividing, you just make a change here. This acceleration due to gravity when the body is at A, and if suppose if you are keeping here g and m value is rho 4 pi by 3 r cube, capital R cube divided by r square. Okay. So again this square and the square from this cube is get cancelled, and you will get the expression as g rho 4 by 3 pi into r. Okay. Now you can take this as equation number 1. Okay. So now you can divide equation 2 by 1. So here g dash upon g dash I want it as g rho 4 by 3 pi r minus x divided by, I have here the g value, g rho 4 by 3 pi r. Okay, g and g, rho and rho, 4 by 3 and pi is get cancelled. Okay, and we will get here r minus x upon r, and after further simplification you will get here r by r is 1 minus x by r. So this is nothing but what? You will get the gravitation, or you can again further simplify g dash is equal to 1 minus x by r into g. So this is the acceleration due to gravity at certain depth x from the surface to the point B, or from center to point B. Okay. So this is what the acceleration due to gravity when you bring the body to certain depth in the earth. Okay. So this is the effect we are getting. So acceleration due to gravity is maximum, always maximum on the surface of the earth, and in rest other condition it is always less. Okay, take a screenshot of this. Take a screenshot of this. I hope everyone is getting this. You all are getting the derivations. Okay, chalo. I hope everyone is took the screenshot. Now the last point, that is at the center. Okay, what is the gravitation at the point at the center R? Okay, so if we consider this diagram and this expression, we can write here, suppose the body which we brought in at the center. Okay, now that body I brought it over here. Okay, so here R is equal to what? X. We are getting R is equal to X. So if you keep here R is equal to X, if I replace G is equal to 1 minus, means X I am replacing by R by R into G. R by R get cancelled and I got 1 minus 1 into G, that is equal to 0. So acceleration due to gravity at the center I am getting how much? 0. So from this we can again conclude the acceleration due to gravity is always maximum at the surface of the earth. Okay, getting? Those who want for the at the center expression, they can take a screenshot of this. Okay, so we are moving towards the next point. So write down one more point, effect of a shape on the earth. So mostly they will ask this question in MCQ. We know that equatorial point and pole. Okay, so what about the masses or radius? That kind of questions we are getting. So effect of a shape of earth. So on gravity on the equatorial plane or at the equator. Okay, we are getting Gm upon Re square, and at the pole acceleration due to gravity at pole Gm upon Rp square. Because here earth we are taking as a spherical shape. Okay, it is not exactly circle, so we have minor and major axis over here. Okay, so at the equator we are getting radius of the equatorial point is always greater, so Re is always greater than the Rp. Okay, means Rp is always smaller. So here we can say that as the radius of the equatorial point is always greater and pole, the radius is always small. So due to that we can say that gravity at the pole is always greater. Okay, it is always greater than the gravity at the equatorial point, because both the points, both the radii are what? Square and divided, so the value will become what? Here less, and the value of gravity become more, so that gravity at the pole is always greater than the equatorial point. Okay, because of, and another reason, that is known as what? Minor axis. Okay, so gravity is always greater at the pole. Getting this point? Note down this or take a screenshot. Sometime they will ask this question for a MCQ. Yeah, MCQ also they can ask, or they can ask 2 mark question also on this. Okay, now next is gravitational field. Okay, gravitational field. So gravitational field. So gravitational field is nothing but the space, or we can say that a space surrounding by the material body, in which its gravitational force of attraction can be measured. Okay, so that is the field, or it is acting on one particular body, so that we can actually measures the gravitational field. Okay, and the force experienced by a unit mass placed at that point in the field. Okay, that is nothing but what? Intensity of the gravitational field. Okay, so here intensity of the gravitational field is nothing but a vector quantity, and that is denoted by E bar, or some people are writing U bar also. Okay, so why I told this definition? Because next point is nothing but gravitational potential energy. Okay, so next is nothing but gravitational potential energy. Very important point. Gravitational potential energy. It is very important point from the exam point of view. Okay, so gravitational potential is nothing but what? The amount of work done in bringing a body from infinity to the point against the gravitational force. Okay, so here suppose we can take, suppose this is what, here here we have the earth, whose radius is nothing but capital R, and whose mass is nothing but capital N. Okay, and a body is in, suppose here I have one body at point A. Okay, and from the center to this A distance is nothing but x. Okay, now I am doing a work. Okay, I am doing a work where at point A, and I am bringing that body to certain distance, somewhere or here. Okay, somewhere or there at point, I will take it as B. Okay, and I am doing small work done to bring that body towards the B, and whenever I am doing the work in the upward direction, so in that case the gravitation is also acting on that body, and gravity is always trying to attract this point B. Okay, so now I took that distance, or yeah, now this is, I took it up to the distance x, or you can take this distance as a small r, and now this from center to this point B is nothing but what? X. So I did a work done against the gravity to bring that charge from A to B. Okay, so this is nothing, this work done is known as what? A gravitational potential energy. Okay, so here gravitation force on a body at point B is nothing but what? Again at point B, that mass is that body came to point B. So what is the force of attraction here, or what is the gravitational force? F is nothing but here G capital M upon small m divided by distance. Distance is nothing but from center to this point B is nothing but what? X square. Okay, so small work done in moving the body from infinity to point A. Okay, so means what? Initially the body, if we take somewhere here at point C, then slowly I did a work done, then that body came to A. Okay, and again I started working on A, then body moves towards the B. So that small work done, dW, work done is nothing but what? Force into displacement. So I can write dw is equal to f into dx. So f I know here, f is nothing but here I have gmm upon x square, gmm upon x square into dx. So this is nothing but your work done. So if we want the total work done or work done in moving the body from infinity to a, so you can take a integration on both the side. So this is 0 to total work done gmm. This is a gravitational constant. Mass of the earth and mass of the body will remain same, so that's what you can take it out. So what is changing here? Distance is changing, because we are doing the work done. Okay, now that body we are moving from infinity to point A, that is nothing but r. Can you getting this? Okay, so if I write it here gmm integration of infinity to r, and x square you can take it up, minus x raised to minus 2 dx. Okay, and you can take a integration x raised to n is nothing but x raised to n plus 1 upon n plus 1 we are getting. So this is what the formula, x raised to n is nothing but we will get x raised to n plus 1 upon n plus 1. But in this case I have integration of x raised to minus 2 dx is nothing but x raised to minus 2 plus 1 upon minus 2 plus 1. That is nothing but x raised to minus 1 upon minus 1. This is nothing but integration of the x raised to minus 2, and then I will take an integration and I will write gmm here. We will get x raised to minus 1 upon minus 1 infinity to r. Okay, and minus 1 you can take it out, gmm, and x raised to minus 1 you can write it as x infinity to r, then you can substitute r over here. So gmm minus sign divided by x, you can put upper limit minus lower limit is here infinity, so leave it, and you can write it as a r, minus gmm upon r, and you will get this as a work done w, and this is also known as a gravitational potential energy, to bring that charge from infinity to certain point. Okay, so this is nothing but what? The work done, and this work done gets stored inside the body as a gravitational potential energy. Okay, and the negative sign shows potential energy of a body is due to attractive force due to earth on a body to bring the body from infinity to certain distance r. Okay, and here that is the reason work is done on the body due to the gravitational field of a earth. Getting this up to here? This is very, very important. This is gravitational potential energy. Gravitational potential energy. Here what we got, the negative sign is that we are doing the work against the gravitational field. That's what the negative sign came. This is very important derivation. Okay, everyone can take a screenshot. Everyone can take a screenshot of this. I hope you all are getting this. Okay, so give the next point, gravitational potential. Okay, gravitational potential. Not potential energy, just gravitational potential. Okay, so what do you mean by gravitational potential? So gravitational potential at any point in the gravitational field of a earth is defined as the amount of work done in bringing a body of unit mass from infinity to that point. Okay, so here we can write V, gravitational potential, which is denoted by letter V. Work done and potential energy, means gravitational potential energy is different and gravitational potential is also different. Okay, so gravitational potential is equal to, we can get here, minus gm upon, we'll get r square. Okay, and here its unit is nothing but joule per kg. Okay, we are getting joule per kg. Okay, so I will repeat this definition again. Here, gravitational potential at a point. Okay, you can write down the definition because very important point. Maybe this question will come for 2 marks. Okay, write down. Gravitational potential at a point in a gravitational field, in a gravitational field of earth. Gravitational field of earth is defined as the amount of work done in bringing a body of unit mass from infinity to that point, okay, and write down V is equal to minus gm upon r square. Okay, and SI unit is joule per kg. Okay, so here one more thing, gravitational potential is always negative. At any point you can take gravitational potential is negative, and as the mass as suppose we can say that here if some object we are moving towards the infinity, then this potential is what become maximum, potential is what becomes zero, that is minimum at infinity, means the body is moving towards the infinity, then potential is what becomes zero. Okay, there is a no field of potential, is very important. Okay, so write down one more point from this. Gravitational potential at a point first, it is always negative, and second point increases as one moves towards infinity, and becomes zero, that is that is maximum at infinity. That is maximum at infinity. Okay. Getting up to here, everyone? Does anyone having any difficulty in the derivations? Everyone is getting the derivations. Is any doubts are there? Okay. So we can move towards the next derivation. Okay. Okay, what we can do first, we can finish the law of period and all, and then we'll go for the escape velocity, then orbital velocity, that points. Okay, so here we have three laws of Kepler's law. We have a three Kepler's law for planetary motion. Okay, so first law is known as a law of orbit, second is known as law of area, and third is known as law of periods. Okay, so we are discussing very first one, that is nothing but law of orbit. Very simple is there, law of orbit. Okay, law of orbit is nothing but what, the each planet revolves around the sun. Okay, each planet is what, revolving around the sun. Of course, it is in the elliptical orbit, because there is a no perfect circle. They are elliptical in nature, so that's what it is, revolving around the sun in the elliptical orbit. Okay, with sun at one focus, means here that planets are assuming sun as a center. Okay, or they are assuming as a focus of a elliptical path. That is nothing but law of orbits. Okay, so I'll repeat this law one more time. Each planet revolves around the sun. Okay, in the circular orbit with sun as a center or focus of a elliptical path. That is nothing but what, law of orbits. Can you getting up to here? Everyone is getting? Is anyone is having doubt, queries in this? Okay. What in the were not clear? What you are not clear with? Okay. Then next law is a law of area. Okay. So just wait. Okay. So what is the law of area? The position of a vector of a planet from sun, that is the line joining the planet to the sun, sweeps out equal areas in equal intervals of a time, or aerial velocity of a planet around the sun always remains constant. Okay, means what, here we are taking sun as a constant. Even we did this during the normal classes. Okay, so here the planet is revolving in the elliptical orbit and they are taking sun as a center. Okay, and here suppose planet is initially here, moving from here to here. So this is what people are thinking, oh, this is a major axis, so it covers this area is maybe more. And when the planet now A to B comes, and whenever suppose the planet is near to the sun, okay, suppose it is again comes from C to D, this area you can feel it's very small, but that is not a light, that is not a thing. Or here whenever same area is covered from moving from C to D. Okay, means here in this law they are saying they are covering equal areas in equal intervals of a time. That is nothing but what? Your law of area. Okay, and last law is nothing but law of periods. The square of the period of any planet about the sun is directly proportional to the cube of the semi-major axis of a elliptical orbit. So we can write here t square is directly proportional to r cube. So we have a derivation for second and third law that we can do it for tomorrow's class. Okay, and in tomorrow's class maybe we can finish the derivations for this chapter. Okay, so I will end this session today. Okay, so I will end this